So we're starting this chapter, Introduction to Convection. This is the precursor to the chapter that deals with external convection, internal convection, natural convection, so like the next three chapters after this one. This is the building block. It's fairly abstract, or it lays the foundation, I should say, for convection analysis. So today we're going to revisit from fluid mechanics the velocity boundary layer. And then we'll also introduce a thermal boundary layer. And those are key concepts in understanding convective flow. Key concepts. And once you have those, we'll talk about the average and local convection coefficient, as well as local and average wall shear stress, which you probably are familiar with out of fluid mechanics. So the idea that you have locally varying property along the surface, as well as average over the surface, is a key concept. Laminar and turbulent flow, I'll get to that a little bit, but we're not going to cover the whole chapter today, so let's get started. So what do we have? We have flow approaching a very thin plate. Thin, flat plate, that's the key idea. So you have the thin, flat plate like this. Maybe I try to show it a little thickness to it, or just show it as a line. The flow is fluid flow coming this way. The flow is approaching it, and it has a uniform profile. Everywhere in this, it has a speed u infinity. So it has no y or z component. We're just talking about a rectangular coordinate system. It's just in the x direction. The flow is in the x direction, approaching this very thin, flat plate. When it gets to the flat plate, what happens to the fluid? What happens to the fluid? Well, the fluid, because of a no-slip boundary condition, the fluid abruptly, and it's kind of a singularity right at the tip of this plate, abruptly stops. But don't worry too much about the tip and the singularity at the tip. Just think of a little distance away. I want to plot what does that velocity look like. Well, it's still out here. It's still u infinity, far above the plate. But close to the plate, or right at the surface of the plate, it has to go to zero because of no slip boundary condition. The plate's not moving. So we have a profile that's flat, far away, and then it has to transition to the equal to zero. So we have the velocity, u, at some location x. What we're going to do is introduce a coordinate system. X runs just like this. X starts at 0 at the leading edge of the plate, and maybe the plate is length L, so that's the trailing edge. The leading edge and trailing edge of the plate, X goes along the axis of the plate. And then the Y direction goes out from 0 out into infinity, out far into the free stream, into the fluid. So that's our coordinate system. So we'll talk about u, the x component of the velocity, at any location x along the plate. When y is equal to 0, that is 0. And then we'll talk about u at any location along the plate. At y goes off to infinity, that has to be equal to u infinity. True? U infinity. But if you plot a few of these profiles, what you find is that there's the presence of the plate is felt further and further into the fluid. So a lot of times we'll sketch something like this, and we'll talk about a distance into the fluid, delta, where the presence of the plate is felt. The velocity everywhere in that region, you can see that in the region y between 0, the surface of the plate, and delta, the thickness of the effect of the plate, the velocity is affected in that region. The velocity is not u infinity anymore. It's less than u infinity. So this gives us the criteria of how thick is that layer of affected fluid called the boundary layer. And so u at any location x, y equal to delta, is and I'm very thankful for this, consistently defined in many, many books throughout the literature as being 99%, 0.99, of the free stream. So if you go out far enough, it'll get to U infinity. But as engineers, we say, hey, if you're 99% within the U infinity, you're there. That's the thickness. That's the convention of the thickness of the boundary layer. Okay. Well, sometimes you can write it as U over U infinity at y equal to delta is equal to 99%. But that's the same idea. Why do we care about flow over plates from fluid mechanics? Well, the fluid has viscosity, and the viscosity affects the transfer of linear momentum through the fluid. Okay, so because of viscosity, you can have some transfer of force or force per unit area through the fluid. What equation gives us that transfer? Tau equal to mu. I'm going to put a partial u with respect to y. All right. So think about a layer of fluid. It's hard to add it to that existing diagram, but here is the location y. And the velocity profile is a little faster on top, then a little slower on the bottom of that cut, that location y of interest. And so the faster fluid exerts a shear stress that pulls the fluid below it in the positive x direction, and vice versa. The fluid below is going a little slower, and it exerts a shear stress in the negative x direction on the fluid above it. Maybe I should draw it like this. Maybe I should say the fluid below feels a shear stress that way. The fluid above feels a shear stress that way. Equal and opposite. Okay. When you pull down all the way to the surface, you can calculate the shear stress at the surface, isn't it? Isn't that mu partial u with respect to y at y equal to 0? And what you have, if you have a plate, you can think about this. That plate, unless I fix it or hold it in place with an external force applied to the plate, maybe a force exerted this way, when the fluid starts flowing over it, it's going to want to sweep that plate to the right, isn't it? Because of the viscosity, the shear stress. So I'm going to have to push or apply a force in the negative x direction to keep it there. And so the shear stress at the surface allows me to calculate how big of a force. And you can think, well, if I have flow over the top half and the bottom half, then I get the average value multiplied by 2. Boom, you got it. You know, I'm sure you've done some calculations like that in fluid mechanics. So what we do is we're very much interested in the shear stress at the surface. Sometimes they'll put C sub F. What? C sub F. It's dimensionless shear stress at the surface. So this was defined as the shear stress at the surface divided by something that gives it a dimensionless quality. So in SI units, shear stress is just like a pressure, force per unit area, isn't it? I need to divide by something that has units of force per unit area. What do we divide by? You could divide by P infinity. Out here, you talk about P infinity, the pressure far away, but you know the pressure doesn't change as it flows over the thing. The pressure infinity is the pressure infinity. It's really not doing much. There's another thing that has the same units as pressure, but it's not the pressure. Give me another term. From memory, from fluids. What did you normalize? Okay. Velocity pressure, dynamic pressure. What is the equation for that? Excellent. Thank you very much. 1/2 rho the U infinity, because that's the appropriate V that stays constant throughout our system, the velocity far away, U infinity squared. Doesn't that have the units of force per unit area? 1/2 rho V squared. Why do we have the 1/2? You could take it out, but the majority of engineering literature leaves it in. 1/2 just helps us with, basically, it's bringing a fluid to rest. And when you bring it to rest, it'll actually boost the pressure. And that pressure is called the dynamic pressure or velocity pressure. They're different names, stagnation pressure. Think different ideas there, but that's now dimensionless. And so you can plot C sub F as well as tau sub S, the shear stress at the wall, as a function of location. We're going to build on that. But I think that's enough introduction to the velocity boundary layer. Now let's talk about the thermal boundary layer. We're still going to have a very thin plate, knife-edged plate. We're going to have it either hot or colder than the fluid. And the fluid's going to be approaching it with the uniform temperature. So let's just say it approaches it at T infinity, and your surface of the plate is at TS. Okay? Now, if the plate is hot, we can sketch that out, that'll work. Or the plate is cold, we can sketch that out, that'll work just as well. Which way do you like? Let's put a hot plate. So just for example, Ts is greater than T infinity. Now, let me just get right to the chase here. We basically were interested in what force is needed to hold that plate stationary, or what is that shearing force that the fluid exerts on that plate as it flows over the plate. In heat transfer, we're going to be interested in what? The flux, Q double prime at that surface, to keep that plate hot. Okay? And then basically what's happening is the convection is sweeping that heat away. It's convecting the energy, the heat transfer through that layer of fluid away. Okay. So force was the idea for the velocity boundary layer. Heat flux is the key idea in the thermal boundary layer. But just like this, if we have a hot surface, we can go out and we can sketch the temperature profile. Maybe I'll sketch it at this location a little bit away from the leading edge, and then maybe I'll sketch it this far, further away from the leading edge, getting toward the trailing edge. And what I want to do is I want to sketch, just like we did right here, temperature is a length of the line in the horizontal direction. That gives us the magnitude, visual image of the temperature. Just like this, magnitude was U infinity, the length of that line for the velocity profile. So we want to start and we want to think about all of these have the same T infinity, the same T infinity far away. But then what happens is it has to get to this surface temperature, which is a length of a line from here to here. It's a little longer, right? Higher surface temperature. That same length of the line from here to here, higher surface temperature. So there's this transition through this layer of slower moving fluid where the temperature profile exists. So what happens is there's the temperature at the surface, and it goes something like that, close to the leading edge. Further away, it's something like that. So you could talk about, the thickness of, or the zone of effect of that fluid has experienced a temperature change because of the presence of the hot plate. It'll be deeper the further you go, and now you have the growth of that zone of effect of the temperature. That's called the thermal boundary layer. Sometimes they'll go back and they'll add another subscript to this boundary layer to say, that's the velocity boundary layer. But I don't think this book does that. I think it's just like if there's no subscript on it, then that's the velocity boundary layer. And if there's a subscript T on it, well, that's the thermal boundary layer. Okay. Well, so you can think of just like this. What is the temperature at X at Y equal to 0? Anywhere along the surface, that's the surface temperature. What's the temperature at X at Y goes off to infinity? T infinity. And so the zone of effect is for Y going between 0 and the thermal boundary layer thickness. How do we define it? Well, in this case, you could say, look at you're going to have a hot surface temperature. Maybe you put the T at some location down the length from the leading edge, where y is equal to the thickness of that boundary layer. That difference between the Ts and T infinity minus Ts is equal to 99%. This equation works regardless if Ts is greater than T infinity or Ts is less than T infinity. It's really focusing on the temperature change between the surface and T infinity, right? And if you plot, they call this a theta. And if you plot theta, let me kind of quickly sketch it here. Don't want to sketch too many of these, but if I plot theta, here's that growth of that boundary layer. Theta is going to actually start at 0 and go to 1. Theta equal to 1. Isn't far away theta equal to 1? Yeah. And isn't at the surface theta always equal to 0? And now you look at it, you say, that's why they like this definition, because when I look over here and I plot u over u infinity, that starts at 0 and goes to 1 as well. So that's nice. Okay, but it's a little more abstract because it's a ratio of temperature differences in the definition of the thermal boundary layer. Well, why do we study the thermal boundary layer? Because we're going to have to predict about this Q double prime. Well, from our convection law, Q double prime coming off of that surface is just the convection coefficient times the hot surface minus the temperature far away, isn't it? But if you also just focus on that stagnant layer right there, if you focus on the stagnant layer right there, it has a temperature profile in that stagnant layer right at the surface. And the only way to get through that layer is conduction. And so Q double prime at the surface is also minus K, the rate of change of temperature with respect to y at y equal to 0. I'll repeat that. That's a concept that's difficult. But it's parallel to this for the viscosity. It says shear stress at the surface. Oh, I need the slope. What is the gradient of the the velocity profile at the surface? Same thing for the heat flux. It is diffusing through heat diffusion, just like linear momentum was diffusing through the momentum. This is diffusing through the thermal conductivity. You have the diffusion of heat. This equation and that equation are combined to get rid of the Q double prime at the surface, and you get an equation for H. What is the equation for H? Well, it's the negative K times the rate of change of temperature with respect to the distance into the fluid evaluated at the surface, divided by Ts minus T infinity. Just like they put a subscript on that delta for the boundary layer thickness, if they put a V, that means definitely velocity V for velocity boundary layer thickness. They'll put a T subscript for thermal boundary layer thickness. Some students will be confused about the property K. K. What's the name of K? Thermal conductivity. And they're going to say, you've got a plate right there, right? And you got fluid above it. Right away in their mind, they have two choices for K. Is it the thermal conductivity of the plate, or is it the thermal conductivity of the fluid? Let me ask you this. Let's go back to viscosity. Is there a viscosity associated with the plate? Not really, but let's say there is. There's a viscosity with the fluid. Yes. There wasn't much choice there, was there? It's like, I know what viscosity it is. It's the viscosity of the fluid, right adjacent, right above the plate, right? Does that help you which K it should be? Which K should it be? fluid. So sometimes they'll put an additional subscript F right there to emphasize, don't put me a solid thermal conductivity right there. You may be tempted, but it's really the gradient of the temperature in the fluid at the surface, and I need to use the thermal conductivity of the fluid. So that gives us a mechanism. If you want, you can rewrite this to be H is equal to K sub F, the thermal conductivity of fluid, the rate of change of theta with respect to y at the surface y equal to 0. It gets rid of that negative sign. All right. So if I go further down the plate, okay, and I try to go, it's still going to go out the same theta equal to 1 far away, but I have more distance to transition. Talk about the steepness of that profile. It's going to be very steep there, isn't it? It's going to be a rapid change in theta as I move away from the plate into the fluid. So this will be greater, larger, near the leading edge. Hence, I have a larger H. I have a larger convection coefficient. Just like you have the steepness of the gradient there, and it's steeper. It's a more rapid change of velocity as I move into the fluid close to the leading edge. Hence, I have a greater shear stress at the surface. Well, that's a lot to swallow, but this is very important concepts for building on it for chapter 6. So let me go back and revisit a few key points. First, let's talk about the plate. Sometimes people will forget that it's a knife-edge plate. Well, what's the opposite of a knife-edge plate? A blunt plate. What would happen if I put a blunt plate in there? Let's say this fluid packet right here, that's not going to feel much. But the fluid packet that's hitting the blunt part of the blunt plate, what's going to happen to it? I need to get around it. So it's going to flow up and over. What's it going to create on that top edge? A separation zone. We don't have anything like that. So some books will emphasize, hey, this is a knife-edged or very thin flat plate, but sometimes not. The next one is it needs to be aligned with the flow. Don't put the flow here and then introduce a coordinate system that's not, X and Y, and it's not aligned. Yes, you can have a hot plate and fluid flow around, something like that, but you're going to get a big, what are they going to call this on the back side? A big wake region. And it's not going to have the velocity profile that we are interested in on the top of that plate. And it's not a curved plate. It's a flat plate. So all these are pretty obvious, but it's not a blunt, it's aligned with the flow, and it's not curved. All right, what about the coordinate system? Well, we boil it down to a rectangular two-dimensional problem. So we're interested in just X and Y as a coordinate system. Where does X start? Leading edge. Often we talk about ending in the analysis at L, the trailing edge, because we have a finite length plate. And Y goes positive from 0 at the surface up into the fluid. So leading edge is kind of a key word. Hopefully you mastered that from fluids. And trailing edge, kind of a key word. And then the plate, we're interested in just analyzing the top half of the plate. If it's symmetrical, then maybe the force needed to hold it there, fluid flow in the top half, bottom half, I have to multiply by 2. But I think you could work out that. But Y goes from 0 up to infinity, and infinity far away, that's the fluid free stream. Good. Let's just summarize what we just talked about for the velocity boundary layer. Velocity is what type of field? It's a vector field. It's a vector field, which means I can think about V is equal to something I plus something J. The notation is standard throughout a lot of engineering literature. It's U is the X component and V is the Y component. What's the other letter for the Z component? UV, K is the letter for in the direction, like I, J, K, U, V, W, U, V, W. But we don't need the W because we're just doing two-dimensional. Okay? So, but when you think about this, that U component is a function of location X down the length of the length of the plate, and Y into the fluid. So U, the X component of the velocity, is a function of X and Y, as well as V. But what we find is the V, no matter where you're at, is much, much smaller than U infinity. So often, that's one of the key observations. There's very little, the flow has to move up, migrate up a little bit. So there's just a little bit of V in there. But mainly V is 0. Free stream, it is 0. Free stream, it's 0. So before the plate and far above the plate, it's just U infinity, I plus 0J. And then at the plate, there's no slip boundary condition. There's a no slip boundary condition. Hence, the velocity of the fluid adjacent to the surface of the plate is the same as the velocity of the plate. And we take the plate to be at rest. So it has 0I and 0U and 0V for velocity. I'm just restating some facts. Help you make it clear. The boundary layer is the zone of effect. Why does it even exist? Because of viscosity. What's happening with the viscosity? Layers that are moving fast exert something on layers that are moving slow, the adjacent layers. So it's a diffusion of linear momentum. It's a transfer of linear momentum. So near the leading edge, what's very steep? It's the rate of change of U with respect to Y. That's huge. This is the rate of change of U with respect to Y at the surface is greater than the rate of, I should put a partial derivative there, the rate of change of U with respect to Y at the surface, but it's further down. It's further down the plate. The slope is steep at the leading edge. The thickness is defined as 99% of the free stream velocity. If I go out and I'm at 99% of the free stream velocity, that's the thickness of the boundary layer. The law of viscosity, this equation applies throughout the domain, and we can apply it in the fluid right at the surface to get the shear stress at the surface. True? That makes sense? All this is just a summary of what we just covered. Then what we can do is we can plot the shear stress as a function of location down from the leading edge to the trailing edge of that plate. Because it's steep velocity gradient early, you're going to have a very high magnitude shear stress early, but it's going to decay or come off lower. See that? This is the shape of the profile. It goes down. What about at x equal to 0? It's a singularity. Let's not worry about it. It blows up. Somehow, mathematically, that fluid that was just happy and flying along at U infinity is now at rest. So we're going to leave it alone. You then have a local skin friction coefficient, C sub f. C sub f of x, sometimes I'll emphasize that this is local by putting a comma x in there. What is that? That's the local shear stress divided by 1/2 rho U infinity squared. Who recalls the name given to 1/2 rho U infinity squared? Dynamic pressure, dynamic velocity, or it's a velocity pressure. Okay. So this also goes to, decreases as further you go down and the thickness of the boundary layer grows. Not only can we talk about local shear stresses, we can talk about the average shear stress. So here they put a bar on top. That's common notation for averaging. How would you average given the local? 1 over L, the integral 0 to L tau dx. Isn't that good for averaging? You could do the same for the average of the skin friction coefficient. If you do that, you'll even see that it's the average skin friction coefficients, the average of the shear stress divided by 1/2 rho U infinity squared. Now let's summarize for the thermal boundary layer. Temperature is not a velocity field, but a scalar field. So we just talk about one value of temperature at a location x and y. It's still two-dimensional rectangular coordinate system. Before the plate and far above the plate, the temperature is T infinity, isn't it? But what happens when we get at the plate, it becomes the surface temperature of the plate. Either Ts is greater or Ts is lower. It doesn't matter which one. I think conceptually, mathematically, most people like the hot plate and the cold fluid. So we introduce a dimensionless temperature difference ratio, theta, and that temperature difference ratio is the same regardless of the hot or cold. And so this always is 1 far away. Theta is 1 in the free stream. And it goes to 0 at the boundary. The no-slip temperature boundary condition, you say, hold it, no-slip temperature boundary condition? It's just basically that the temperature of the fluid adjacent to the solid is the same temperature as the solid surface. Right here it is. Meaning that the dimensionless temperature difference ratio is 0 at the surface. And the definition of the boundary layer, 99%. Continuing a discussion of the thermal, we find that it's steeper closer to the leading edge and not as steep farther away. You can combine both a global or macroscopic equation for the heat flux, which has H, and we want to get an equation for H embedded in it. Okay, that's the goal. With Fourier's law, and you get that H local is K sub F. Why that subscript F on that K? It's the fluid conductivity. How many times you give a problem and you'll have, okay, here's the conductivity of the solid, and the student will grab that and use it. It's not the right K, right? dt dx, dt d theta dy at the surface. And you could then take the local, average it over the length. Make sense? We have some time for some problems. Let's solve this problem. So we have air at 107 degrees C flowing with a velocity of 0.056 meters per second over a knife edge flat plate, and the surface of the plate is kept at 47 degrees C. The temperature distribution in the boundary layer is given by this equation. So we take a look at this equation. This looks like our theta, isn't it? And this is just 1 minus an exponential of some terms. This is a y, so you could see that they're really giving you theta as a function of y. True? Okay. And what's this? U infinity. That's U infinity right here, given. Nu. What is nu? That's at kinematic viscosity, one of those viscosities. It was mu over rho from definition. Kinematic viscosity is dynamic viscosity or absolute viscosity. The first viscosity, mu, has two names, dynamic or absolute viscosity. You divide it by rho, you get the kinematic viscosity. And then PR, Prandtl number, and they just tell you here's the number. It's the Prandtl number and its value is 0.7. So they tell you the thermal conductivity to use. That's a fluid property. The Prandtl number is a fluid property. The kinematic viscosity is a fluid property. They give you the temperature profile in the boundary layer. All right. Calculate the surface heat flux. What? And then calculate the convection coefficient. I'm going to stop and see how far you can get on that. All right, so we'll pick it back up here. So how do I calculate the surface heat flux? Isn't that Q double prime at the surface? And I think you had it. What did you use in words? The blah, blah, blah's equation. That was the part. B is for H, the convection coefficient. But if I just wanted the surface heat flux, what's coming? So minus K sub F partial T with respect to y at y equal to 0. And you could say, hey, we can turn this into minus k, or k sub f times theta, but you can just do this. If this is your temperature difference, can you get, in general, can you differentiate that equation to get first just the derivative temperature with respect to y? Wouldn't that start by bringing over T infinity minus Ts? And then you would have this derivative of 1 minus exponential blah, blah. But if I take the derivative of 1, that falls out to 0. And then I have minus exponential of something times y. So that minus and that minus are going to work to create a plus. It'll be the Prandtl number u infinity over nu times e to the minus Prandtl number u infinity y over nu. Did I do that derivative okay? And once I do the derivative okay, then I say evaluate that at what location? Y equal to 0. So I'll pick up T infinity minus Ts, the Prandtl number times u infinity divided by nu. E to the 0 is 1. E to the 0 is 1. So Q double prime at the surface is equal to minus thermal conductivity of the fluid times the temperature difference, T infinity minus Ts, times the Prandtl number, u infinity, divided by the kinematic viscosity. So we substitute numbers, and we get Q double prime at the surface is a negative 3,660 watts per meter squared. And I strongly encourage you to substitute numbers, chase your units, making sure the units give you the right answer. And why is this negative? It's negative because it's a hot fluid flowing heat into a colder plate. And the way we wrote that equation was the hot plate with the transfer out. But that's all it is. It's negative indicate the heat flux. Flux is into the plate. That's all. Okay. What about the convection coefficient H? Well, we go back to our global equation. Isn't Q double prime surface equal to H times T? The way you write it, you could put Ts minus T infinity. You're saying, oh, I have a hot plate and it's pushing it out into the fluid. That's great. So we have H is equal to Q double prime S divided by, I'm going to put a negative, I'm going to put T infinity minus Ts. So it'll get rid of that negative on the Q double prime that we calculated. And you have T infinity is greater, it's 107, minus the surface, 47. And you get H of 61 watts per meter squared degree C. That's the answer to part B. That's a bad looking H, isn't it? Let's make it a little cleaner. H. Any questions about that? Yes, sir.
What do you have a negative sign in front of the flux?
Yeah, I do, because it just basically says, the way I wrote it was moving from the solid into the fluid, but the fluid's warmer than the solid. Right? Because what's this? It's saying from the solid into the fluid with that minus sign. And so I just left it there. I'm going to go ahead and stop, and we'll go ahead and get your exams back.